Our lesson today is on vector proofs. So we've done a lot now with vectors. We know scalar multiplication, we know addition, we know subtraction. What we're looking at is the idea that we can try and prove geometric properties using vectors. So we're only going to do two examples today. So relatively short note, I suppose. But this is looking at a topic that we're not as familiar with. So we did one proof the other day. We're going to try two more today. And then there's just some practice questions for you to try. They're all trying to prove geometric properties. So what I'm giving you to start is a description of a scenario and what we're trying to prove. So prove that the line joining the midpoints of two sides of a triangle is parallel to the third side and half of its length. So we need a diagram for that first. Prove that the line joining the midpoints of two sides of a triangle. So I'm going to draw a triangle, just any old triangle. It says the line joining the midpoints of two of the sides. So I can put a midpoint here and a midpoint there. And I can put some dashes because I know those are midpoints. Prove that the line joining those midpoints, so the line from there to there, I want to prove that it's parallel to the third side. So this one's parallel to that one. That's what I'm trying to prove. So I can't actually put that in there, but that's my goal, okay? I'm trying to show that they're parallel and also that it's half the length. So that's our goal with the proof. Can we try and do that with vectors? Well, as it's drawn, it's hard to refer to a vector, so I'm going to put some letters on so that we can actually refer to something. So call it triangle ABC, and then call our midpoints M and N. Now, one of the things we have to think about, there wasn't actually a statement here to prove, at least not geometrically, it wasn't stated. We have to figure out what's necessary to prove. If we're trying to prove that the green line is parallel to the bottom line and half the length, what would that look like in terms of vectors? Well, we need to state a vector. So our goal would be to prove that vector BC, for example, so the vector at the bottom, compared to vector MN, BC should be twice as big. So that's what I need to prove. Can I prove that vector BC is actually exactly the same as two vector MNs? That's the hope. And if I can do that, it's saying two things, right? If the fact that the 2 is there means it's a multiple of each other, means they've got to be the same direction. And the fact that it's specifically a 2 means that BC is double the length of MN. Now to prove this, remember we talked about proofs a little bit the other day. It's kind of like a trig identity. We're trying to show that one thing is equal to something else. What we want to do is we want to start with one of those two sides. So either start with BC or start with the 2MN, and then show eventually that one is equal to the other. I think in this case, and this is just, it would have worked either way, but if we start with the right-hand side, I think that's going to be a little bit easier for us. So I'm going to start with that. We're going to try and do some work here, and I'm hoping that my final line is going to say this. Okay, that's the goal. Can we get that far? Get rid of that. That's what we're working towards. So I have two vector MNs. Remember, as we're doing a proof, our goal is to show as much as possible, trying to make the proof as obvious as possible. So there are lots of different ways that I can write this, but here's one. And again, keep in mind, this is a new idea for you. So whether or not you see all of this right away is okay. We're still learning it, still getting the hang of it. The hope is that after we've done a couple of them, when you start working on the practice questions, you'll start to have some ideas. Things that we're allowed to do. We're allowed to change one vector into the sum of other vectors, or vice versa. We can add vectors together. We can replace equal vectors, which looks like it might be useful here since we have midpoints. So first thing we can do, we've started with something relatively small. We've got two vector MNs. what I'm thinking is let's change vector mn into the sum of something. So what I'm going to try is I'm going to take vector mn and I'm going to make it into those two vectors, m to a and a to n. So I'll write it this way. In brackets, mn is changing into ma plus an. And what you're hoping again is that we look at that and go, oh yeah, I can see what's happened there. And notice I needed the brackets. Brackets had to be there because the 2 applies to everything inside the brackets. What I want to do now is I'm going to distribute that 2. Remember, one of our rules we looked at was that vectors are distributive. We're allowed to multiply this through the bracket. So in a sense, I'm just taking that 2 and multiplying it by vector ma and multiplying it by vector an. Okay, well now I have 2 vector MAs. And I know that MA is the midpoint of that whole line on the left. So what I can do is I can change that 2MA into just vector BA. And that was because point M was the midpoint. I'm allowed to do that. Exact same on the other side. I have vector AN. Since N was the midpoint, 2 ANs is the same as vector AC. And now I have this. I've got vector BA all the way up and vector BC, or sorry, AC all the way down. If I put those together, it gives us vector BC, which is what we needed. So our proof is completed, which is basically what QED means. It's mathematical symbols meaning therefore proven. We've proven what we were set out to prove. Again, not the only way to do it. We could have done it even if we'd started with vector BC, and basically we would have just constructed this proof in exactly opposite order. We would have done everything in exactly the backward steps, and that would have worked fine too. There were a couple other things we could have tried. One of the things you'll notice is it's very possible to start off with something and it doesn't actually help. So sometimes, like a trig identity, right? We'll try something and it turns out it didn't work that well in the end anyway. Let's try our next one. It says ABCD is a parallelogram. Points P and Q trisect the diagonal AC. Prove that DPBQ is a parallelogram. So we always have to be careful with what we're allowed to assume, right? It tells us that ABCD is a parallelogram. So I can start with that. Here's A, B, C, D. Notice, I'm not sure if we would have mentioned this to you many times before. When we say ABCD is a parallelogram, that's in order. So corner A first, and then go to corner B, go to corner C, go to corner D. So it wouldn't have been right if I had labeled it this way. If I had done this, that wouldn't have matched the description. Okay. So the ABCD all go in the same order. In this case, I've got it drawn clockwise. You could have gone counterclockwise, and that's fine too. Okay, not my best picture, but there's a parallelogram. I can do this. Since it's a parallelogram, opposite sides are equal and parallel. So I know that, right? That's something that I know. That means, for example, that vector AB and vector DC are equal. That's kind of helpful. Points P and Q trisect the diagonal AC. So I have to draw the diagonal in from A to C. And points P and Q trisect it. So I think you know what bisect means, right? Bisect means cut in half. Trisect would be cut into 3 equal pieces. Yeah, that's relatively close. So there's point P, there's point Q, and these are all equal to each other. Trisected it. Prove that dp BQ is a parallelogram. So D to P to B to Q and then back again. Prove that that's a parallelogram. So I can't assume it, right? I can't put any of the dashes on there, but I'm trying to prove that it's a parallelogram, which is actually kind of a neat property, by the way. Anytime I say prove one of these, it's true. Okay, so you don't worry about trying to say, no, that's not right. It's right. It works. We just have to figure out a way to prove it. This is kind of a neat thing, right? We can construct a parallelogram this way. Start with one parallelogram, and by trisecting a diagonal, we can create another one. What would be needed to prove that DPBQ actually is a parallelogram? We have to think about what's required for a parallelogram. The requirements to be a parallelogram are that opposite sides are parallel and equal to each other, right? Opposite sides are parallel and equal. So what we need to prove opposite sides are parallel and equal, or sorry, parallel and the same length. That's exactly saying that opposite sides are equal vectors, isn't it? So we want to prove that vector PB and the opposite side to that would be DC. We just want to prove that those are equal. And then similarly, on the other side, DP is equal to QB. Now, there is a bit of an argument there. If we could actually convince ourselves that one of those is true, that PB is equal to DC, that forces the other two sides to also be equal vectors. That's probably actually more difficult to write down to explain why that has to be true than it will be to simply prove both statements. So I'm just going to prove both statements, because if you can do one, you'll get the other one in exactly the same way. So I'm going to start with the one on the top there. I'm going to try and prove that vector PB is equal to vector DC. So how are we going to do that? PB is here, and we have to think about what we might do with it. Notice I've written that down wrong, haven't I? It's not vector DC, I want vector DQ. That's an easy fix. There. Someone would have told me that if you guys were in class. So prove that PB is equal to DQ. And we can't just assume it, right? I know it looks like it in the picture, but we can't assume it. We have to prove that it's true. So what can we do? We have to change PB into something else. And there are tons of options here. So with the more practice with this, you'll start to get ideas of what a better choice would be. For example, if I wanted to, I could change vector PB into BC plus CB. That would work. Okay, let me write that down. I could do this. Okay, that's an option. Right, that's one thing that would work. If I really wanted to, I could do this. I could do PQ plus QC plus CD plus DA plus AE. So I've gone like all the way around that shape, created this massive thing, and it would be a mess. But it's true, right? This is an absolutely true statement. It's just created more of a mess than it's worth. So picking a good choice is part of the challenge in this. In this case, I only want to change it into two vectors. I'm going to change it into vector PA plus AB. Okay, again, maybe not obvious, but it seems like kind of the simplest exchange we can make. It's a reasonable place to start, and then it turns out it'll work for us. So I've turned one vector into two. Now I want to see what I can do with vector PA and vector AB. AB might be the easiest one to think about first, because we're limited to what we can do. AB is at the top, and remember the black shape that I have there we know is a parallelogram, so AB is the same as vector DC. So I can put that in. Change vector AB into vector DC. It's not a very good D. then PA, I've got a couple of choices there. PA is one of those trisected lengths. So PA is the same as QP. It's also the same as CQ, and that's the one we want to choose because it's closer to what we're trying to get in the end. So I'm going to change vector PA into vector CQ. And now we're really close. We have those two vectors. They both have C's in them, so I'm just going to rearrange it. I'm going to bad D again. There we go. Vector DC plus vector CQ. And now those two vectors are aligned head to tail, so the C is accordion, and we get vector DQ, which is what we were trying to get in the first place. Okay, so we've got that one. This one is now correct. We've proven the first statement. Can we prove the second statement? Well, it should work out exactly the same way. We're going to start with vector DP, and I want to change it into QB. So see if you can do this one. Okay, pause the video if you want to, see if you can produce this one without me showing you yet. Vector DP, I'm going to change into vector DA plus vector AP. And then I'm going to replace some equal vectors. DA is the same as CB, and AP is the same as QC. So I have my two vectors. They aren't aligned right, though. I'm going to change the order. Remember, this is an important step. I think it's reasonable to see. Let me write it down so I can point to it. I think it's reasonable to see how you would go straight from this step to this step. Okay, I'm not saying you guys aren't capable of seeing that. What I am saying is that we're trying to prove it. We're trying to make it as obvious as possible. And so this step right here should still be there. We're trying to be as obvious about everything as possible. That step is now correct. So now we've proven both. So now we are done. One thing we see occasionally on vector proofs is people make stuff up at the end, right? Just all of a sudden say, oh, it's equal. Well, by being as specific as possible and trying to show every single step, you can't really do that, right? You have to be really specific. Okay, there's our two. So there's a worksheet for you to work on. I can't remember exactly how many questions there are, but there's some good ones. And they'll vary in difficulty. The first couple aren't too bad, and the ones towards the end get a little bit trickier. I've posted the solutions, so you can see those. But don't look at the solutions too quick. It's really important that you give these a try. It's the type of question where if you don't practice them yourself, you'll never get better at them. You need to experience what it's like to try something and get it wrong, and then try something again, just like trig identities. You need to get used to how to show your work. So even if you do work through all of them and you feel like you've got them all, then please do still check the solutions and make sure that everything looks right. Make sure you've set things up properly, because there's certain things with proofs that we shouldn't do. Okay, for example, sorry, this is now wrong. Okay, I'm going to erase this for a minute. It would have been a very bad proof to start like this. This is my first statement again. It would have been a very bad proof to even just write that down and then keep going. Right? I mean, it looks similar to what we did before. If I had done that and then even changed DQ into DC plus CQ, this is really bad form for a proof. And it's sort of a situation where you knew what you were doing, but it's just very bad form. So please don't ever start with a line like that where you're saying things are equal. You're trying to prove that they're equal, so you can't start with it. Okay, that's it. Give it a try. If you got any questions, let me know.